Let us look at some more examples of groups. Can we say that the set of natural numbers under addition forms a group? Let's bring in the Kelly table, and this dot 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 represents continuation of the same pattern with respect to the rows and columns. Now here, let's take the axioms one by one. Closure property, A plus B, take any two natural number, add them up, and you will get another number which is also a natural number. So that means it is closed under addition. What about associativity? Now here, we cannot look at the Kelly table and say, okay, it is associative. But based on our previous learnings, we know that natural numbers are associative under addition. Okay, what about identity? Now, is there a number such that when we add it to any number in the set of natural numbers, we get the number itself? No, we don't have. Now here, remember, I'm assuming that 0 is not in the set of natural numbers. So basically, I'm making a distinction between whole numbers and natural numbers. So there is no identity element. What about inverses? See, the point is, if there is no identity, there can't be a inverse. Let's look at the statement itself. There does not exist an inverse of A in the natural numbers such that A plus minus A is equal to E. So here minus A is the additive inverse. So when we are talking of additive inverse, we write it like this. And in general, when we talk of inverses, we write it in this form. So since there is no identity, there can't be any inverses. So which means the natural numbers do not form a group under addition. Now let's look at the second example. Can we say that the set of integers under addition forms a group? Again, let's bring in the Kelly table. What about closure property or closure axiom? A plus B equal to C. You will notice that you take any number, add it to any other number, you will get a number which is also there in the set of integers. So it is closed under addition. Associativity, we know it is associative. What about identity? Yes, E equal to 0. So the identity element is 0 because you add E or 0 to any number, you will get the number itself. What about inverses? Yes, for every element in the set, you have its negative, which when added will give you 0, the identity element. So that means integers under addition form a group. Thus, integers under multiplication form a group. Let's bring in the Kelly table. Is it closed under multiplication? Yes. Is it associative? Yes. Is there an identity element? A times E equal to E times A is equal to A. Yes. E equal to 1 is the identity element. What about inverses? Only 1 and minus 1 have multiplicative inverses in the set of integers. All other integers have either inverses outside the set of integers or no inverse at all. For example, no inverse at all is for 0. 0 has no multiplicative inverse. So that was the set of integers under multiplication. Because no inverses exist except for one or two elements, we can say it does not form a group. Now this is called the quaternion group, and its Kelly table is this. So the qubit set the unit set contains 1, I, j, k, minus I, minus j, minus k, and minus 1. And it has certain special multiplicative rules. That is why I put this in a circle. I square is minus 1, j square is minus 1, k square is minus 1, minus I times minus I is minus 1, minus j times minus j is minus 1. So go through this and you will understand the rules of the multiplication in the quaternion. Keeping those rules in mind, closure, yes. Associativity, yes. Identity, yes. E equal to 1 is the identity. Inverses. For all A, there exists an inverse of A in the quaternion set, unit quaternion set, such that A times A inverse is equal to 1. So this forms a group. If you want a little bit more detail about the rules of this multiplication, please download the book and have a look at it. And Q8 is non-abelian. Now remember, we have seen that if across the main diagonal, if it is symmetric, it is abelian. If it is not symmetric, it is non-abelian. So just look at this. 1, I, great. J, great. K minus K, and then we have K. So actually it should have been minus K. So that means it is not symmetric across the main diagonal. First instance you reach, you can stop going further. So it is non-abelian. Now let's see whether cube roots of 1 under multiplication forms a group. What are the cube roots of 1? It is 1, of course, I have not mentioned it, but it is also this and its complex conjugate. So this is represented by omega, this is represented by omega square. Because when we square this, we get this. Okay. So let's see whether this forms a group. Again, let's bring in the Cayley table. 1 times 1 is 1. 1 times omega is omega. 1 times omega square is omega square. Omega times omega is omega square. Omega times omega square is equal to 1. Omega square times omega square is omega. So which means the set of cube roots of unity under multiplication is cyclic and the generators are omega and omega square. You can take omega, keep taking the powers of it. You will get all these elements. Similarly, you take omega square, keep taking higher and higher powers of it, and you will get all these elements. So that's why they are called generators. Okay, now let's see first whether it forms a group or not based on the axioms. So closure, A times B is equal to C. As we just now discussed, multiply any of these, you will get another cube root of unity. So closed under multiplication. Associativity, yes. Identity, yes. E equal to 1. By the way, 1 is not the generator because you take any power of 1, it will give you 1 itself. What about inverse? For all A in the set of cube roots of unity, there exists an inverse of A in the set such that A times A inverse equal to 1. So inverses, yes. So that means cube roots of unity under multiplication forms a group. Now let's see S3. Let's say it is the set of permutations of 1, 2, 3 under composition of permutations. So here that circle represents composition of permutations. As usual, let's bring in the Kelly table. Empty brackets represents the fact that we don't do anything. So whatever number it is, if we compose it with this, it will not change the order of the individual numbers. So again, let's see closure for all A comma B in S3. A composition B will also be in S. So it is closed under composition of permutations. You can go through this and see and make sure that you have understood. Associativity, yes. Identity, there exists E equal to no action in S3 such that A times no action equal to no action times, I'm saying times, it should be composition of permutation. Composition A is equal to A. So identity exists. What about inverses? For all A in S3, there exists an inverse in S3 such that when we compose them together, we get the identity element. So inverses, yes. That means the set of permutations of three numbers under composition of permutations is a group. So that was some examples of groups. As we go along, we will look at more examples. So there are very interesting groups ahead. So that's it for now. But before I leave, let me remind you there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.